Howdy, howdy. So, to go over another concept is Q, which is maybe a ratio of the components when they may or may not be at equilibrium. So Q is a different kind of monster than K sub C or K sub P. So we're going to calculate Q, and we're going to determine, based on the value of Q, when we compare it to K sub C or K sub P, when we compare it to that, we can actually predict which way the reaction is going to shift towards the products or reactants. So we are given a problem here. N2 plus 3H2 is in equilibrium with 2 ammonias, and we're given a K sub P at a certain temperature. So we need to calculate the Q4, and I changed the numbers here because I realized that I did part A and on the video chat already. So let's try part C. So calculate Q for a mixture of 13 atmospheres of NH3, 27 of N2, and 82 of H2. So let's calculate Q for that. And then we're going to do a little bonus here. We're going to actually, to practice, we're going to calculate K sub C for the reaction. So if we're given a K sub P, let's go ahead and calculate K sub C too. Why not? So that's just a little extra fun thing. So if we were to set up the K sub P equation, K sub P is going to equal the pressures of NH3 squared. So divided by the pressures of N2. Ooh, that's a weird bracket. Times the concentration, the pressure of H2 cubed. I know I'm using brackets here, but that's just a habit. Cubed. Okay, so let's plug in our pressures here, and then we will be able to find a K sub P. So pressures are for NH3, so we're going to have the K sub P is going to really be equal to whatever 13 squared is, or sorry, the Q. Sorry, the Q. And why is this a Q? Because we don't know if these numbers are at equilibrium just yet. We're going to actually find that out. So it's going to be 13 squared divided by whatever 27 times our H2 value, which is 82 cubed is. So we're going to do some tippy typing in our calculator. 13 squared is 169 divided by ooh, that's a big number, isn't it? Divided by 1488636. So then uh, 59 divided by, I'm sorry guys, 169. I do not have a good calculator. So I got 1.136 or 1.135 times 10 to the negative 5, and that is my Q. So let's compare that to the K sub P. So the Q in this case is smaller than the K, right? So our Q is too small. So when you look at a fraction, right, you have your numerator and you have your denominator. If something is too small, which is too big? The denominator is too big. You're dividing by too big of a number. So what's in the denominator? What is the denominator? The denominator is the reactants. So it's not the denominator's too big, so we have too many of these, which are the reactants. So we have too many of this. So which way is it going to shift? So it will shift right. So it will, if we were to combine this amount of ammonia, this amount of nitrogen, this amount of hydrogen in a container, it would sit there, and then eventually we would expect to be getting more NH3 produced and a little bit less of these being produced, or a little bit less of these present. So that's what we would be expecting. So since, if you guys notice, I did not at any point memorize if Q is less than K, then it will shift right. I like to look at it and understand what those numbers actually represent. I think that just makes things a little bit easier. So, bonus, let's calculate K sub C for the reaction, because this is something that I could and will ask you on the exam. So the equation is K sub P is going to equal K sub C times R times T times delta N. And so the R in this case is, I'm going to double check. The R in this case, I believe, is the gas constant 0.08206. Remember, there's a couple different ones. And T has to be in Kelvin. So in our problem, we are not in Kelvin. So if we added 273 to that, we're really talking about 723 Kelvin, right? So K sub P, which is 4.51 times 10 to the negative 5, is equal to our unknown K sub C times 0.08206. Man, I get some sloppy work, don't I? Maybe I'll start it on a new page. How about that? We are flying by the seat of our pants, people. Buckle up. So K sub P, our K sub P is 4.51 times 10 to the negative 5. And that's going to equal our unknown K sub C times 0.08206. And then we determine 723 for Kelvin. And then we have our delta N. So it's going to be final minus initial. Number of gas molecules, essentially. Moles of gas, if you will. So our final moles of gas, we have 2. And our initial, our reactants, are 4. So it's going to be 2 minus 4. So it's going to be number of gas mole product minus number of gas mole reactant. So for us, it is 2 minus 4, so negative 2. So it's to the power of negative 2. Not so shabby. So let's start making these things look a little bit nice. So 0.08206 times 723, we get right? And if we did that to the power of negative 2, we would get 2.841 times 10 to the negative 4. Okay. And to solve for K sub C, simply divide 4.51 times 10 to the negative 5. Oh, sorry. This is making me wish I brought my calculator back from the office. Times 10 to the negative 4. I get K sub C equals, and that's a capital K, right? Equals 0.1587. So, if our number of moles was 0 of gas change, RT to the power of 0 would be 1. So K sub P would equal K sub C. Also, what if we had no gases, right? What if this was just an aqueous equilibrium? This would also be 0. So those are two situations where we have 0 as a change. So again, we looked at Q. We were able to determine a Q based on given reactants and given products. And then we were able to look at the amount of Q compared to the K sub C, or K sub P, if you will, and say, oh, since Q is smaller, we must have too much, whatever's in the denominator, what's in the denominator? We must have too much reactants. So the product's going to shift, or the reaction's going to shift to the right, make more products. And then we also calculated the K sub C for the reaction, since we were given the K sub B. Good luck!